Hi, and welcome to module number 39. Recall that in module number 38, not only were we discussing um, the support vector machines, we also concluded the machine learning material. Now we're going to have 10 or so modules on sparse signal processing. So we're going to begin in this module by trying to understand what is sparsity. So we begin with the concept that we've seen before, a signal x, and we can plot x as having a horizontal axis, which corresponds to time, and a vertical axis, which corresponds to amplitude. I'll just abbreviate that by AMPL. And x can often be decomposed into a summation of alpha I, psi I, where the alpha i's are coefficients, and the psi i's are elements of our representation. Our representation overall is denoted by psi, and this could be an orthonormal basis. We'll talk about that, I believe, in the next module, or it could be a tight frame. We're also going to cover that concept. And some examples of orthonormal bases and tight frames are a spike basis, where each of the vectors is non-zero only at one location, or Fourier sinusoids, wavelets, and other types of representations. Here are graphically illustrations of Fourier types of sinusoids. And again, x is a linear combination of the psi i's, the basis vectors. Now, the coefficient alpha I is a projection, an inner product of x onto an orthonormal or ON basis function psi I. So we can express that alpha I is an inner product between x and phi I. Inner product is denoted by these angles. Examples could be fast Fourier transform, DCT wavelet transforms, and so on. But the key here is that oftentimes for many types of signals, many of these coefficients are close to zero. And that brings up the concept of sparsity. For maximum efficiency, we want to choose a basis such that most of these coefficients are going to be close to zero, and just a few of them are going to be large. Now, sometimes you have a set of data x that x is unstructured and it's hard to do so. But other times we have maybe images or video or audio signals for which there exist representations, psi matrices or psi structures that sparsify the signal. One example would be that smooth signals are sparsified by Fourier sinusoids. Another example is that piecewise smooth signals are well represented by wavelets. So this brings up, now that we have the understanding that there are classes of signals, and we're going to see an example soon, classes of signals that are sparsified by some well-chosen representations, let's talk about how to approximate a signal with respect to a representation psi. So we have n basis elements in total, and we're going to quantize or encode the coefficient sizes, and moreover, we're going to only keep the k largest terms and throw away the rest. So not only do we need to spend bits encoding the quantized coefficients, the k largest ones, we also need to spend bits on encoding where those k are actually located. So earlier, we were saying that x was equal to a linear combination of alpha I, psi I. And now we're saying that x hat, our approximation to x, is equal to a summation of the k largest terms, and each of the alpha i's is now quantized to alpha I q, q for quantization. This is known as a nonlinear approximation, and recall that a linear approximation has the style that you're always looking at the same coefficients, the same i's. For example, oftentimes in undergrad signal processing, there are concepts of filters where some of the frequencies are going to be magnified and others are going to be perhaps attenuated and others are going to be entirely removed. So the amplification coefficients could be perhaps 2, 0.3, and 0. And you're going to have the same coefficients magnified by 2 or attenuated by 0.3 and so on. But in nonlinear approximation, again, what I just described is linear. What I just described can be expressed as a linear operator, and what I specifically, the type of filter that I described is a convolution, which is a linear operator. Here, it is a nonlinear approximation. We're modifying the coefficients not standalone, but the type of modification depends not just on the magnitude of our coefficient, but also potentially the magnitudes of the other coefficients, because we need to look at the k largest ones. So why are we interested in this nonlinear approximation instead of a linear approximation that keeps the same coefficients for each signal? The nonlinear version that keeps the k biggest ones can offer us better approximation quality for the same number of terms. So here we have an illustration with 3 different panels. The 3 different panels correspond to 3 versions of the same signal. The top panel is the original signal, and the horizontal axis is time, the vertical axis is amplitude. And an interesting feature of this signal is that, first of all, there are significant discontinuities. There are also discontinuities in the derivatives, and the areas between the discontinuities are smooth. Now, we have a linear approximation with 80 coefficients. Overall, the number of samples for this original signal seems to be somewhat greater than 1,000, probably 1,024. And with 80 coefficients, we get the smooth areas rather well, but the areas with either discontinuities or discontinuities in the derivative are smoothed out. So we lose quite a lot of information there. On the other hand, the nonlinear approximation with the same number of coefficients, 80 coefficients, provides better fidelity around these discontinuities. So the take-home point here is that for the same number of coefficients, nonlinear is better. Now, we're paying a price. We need to encode the locations of the k largest ones, but that price, as you can see, is often worthwhile. So here's an example that this is not an abstract concept, but there are lots of signals that actually are sparse with respect to some well-chosen representation or basis. Our upper 2 panels are going to represent an image example. The left top panel is an image of a cameraman on the MIT campus, and there are n pixels. And the upper right-hand panel are wavelet coefficients that correspond to that pixel. The dark blue coefficients correspond to wavelet coefficients that are close to 0. The brighter colors, in particular the yellows and the reds, correspond to wavelet coefficients with larger amplitudes. And first of all, you can see that within this panel, in the corner which is on the top and toward the left, that's where we have the low pass type of information. That's where we tend to have a lot of larger coefficients. And at the higher frequencies, when we'll discuss wavelets, we'll see that this is also called higher resolution. We tend to have the larger wavelet coefficients clustered around edges in the image. But the big picture is as follows. We had n pixels. We now have k significant wavelet coefficients. K is much smaller than n, and the large majority of wavelet coefficients are the blues. They're close to 0. That's a first example, an imaging example. And the second example, an acoustic example, is the chirp of a bat. And what you're seeing in the left panel is the signal in the time domain. The horizontal axis is time. The vertical axis is the amplitude of the signal. And it looks rather jagged and perhaps complicated. But on the right lower panel, you're seeing Gabor coefficients for this bat acoustic signal. Gabor coefficients have the feature that they're localized both in frequency and in time. And here the horizontal axis again is time, and the vertical axis is instantaneous frequency. Again, they're localized both in frequency and in time, and we're going to discuss this type of localization when we discuss wavelets in a few modules. And as we move to the right, the location where the frequencies are centered is moving down. But overall, the large majority of these Gabor coefficients are dark blue, close to 0, and we only have these 3 different regions where we have some larger Gabor coefficients. So once again, K large coefficients, and the overwhelming majority of the coefficients are going to be close to 0. So this gives rise to the idea of transform coding. It's a conventional approach in signal processing to sensing and compressing a signal. We have an input X, we sample it n times, and we compress it. By compressing, that means that we compute projections of the signal X, the n samples, with respect to n basis vectors. We identify the K largest ones, and we transmit them. On the receiver side, we take a linear combination of the K largest coefficients, or of course, and the basis elements that they correspond to, and that gives us X hat. So compression here is a sort of transform where we need to sort the coefficients, we encode the K largest. This requires quite a bit of computation, and most computation in this conventional signal processing paradigm is performed at the sensor. And this is an asymmetrical system because the decoding side is actually lightweight. All it does is form a linear combination from these K coefficients. And not only is it asymmetric, meaning more work at the encoder, in many signal processing systems, the encoder is battery operated, whereas the encoder, you're often sitting perhaps next to a television or a desktop, something like that. So you have much more computational and power and energy. And we're doing all of this work, all of this sampling, just to throw away a large majority of the coefficients, 80, 90% typically. And what we're going to see overall in the sparse signal processing material is ideas of sparsity that lead to more efficient signal acquisition and sparse signal processing. That'll be it for this module.